Hello and welcome to my presentation. My name is Janelle Stradford, and today I will be presenting my project on fake news detection using natural language processing and machine learning techniques. This project focuses on building and comparing multiple models to automatically classify news articles as either real or fake, and evaluating not just their accuracy, but also their confidence and strength in real-world scenarios. Fake news has become a significant issue in today's digital world. With the rise of social media and online platforms, misinformation can spread extremely quickly and reach large audiences within minutes. This has serious implications across multiple areas, including politics, public health, and financial markets. For example, misleading information can influence elections, create panic during health crises, and even impact stock prices. Because of the speed and volume of information being shared, it is not feasible to manually verify all content. This creates a strong need for an automated system that can detect and classify fake news effectively and at a large scale. The project's objective. The main objective of this project was to develop a system that can classify news articles as either real or fake. To accomplish this, I implemented and compared three different approaches: logistic regression, which serves as a baseline model; a long-term memory neural network, which captures sequential patterns in text; and a transformer-based model from Hugging Face, which represents a more advanced state-of-the-art approach. As shown in the diagram, the system takes in a news article, pre-processes the text through cleaning and tokenization, and then converts it into numerical features. And then it passes it into a model to generate a prediction. In addition to accuracy, I evaluated the models based on prediction, confidence, and sensitivity to borderline or ambiguous examples, since these are important factors in real-world application. The dataset. The dataset used in this project consists of several thousand labeled news articles collected from publicly available sources such as Kaggle and UCI Machine Learning Repository. Each data point includes the full text of a news article and a label indicating whether it is real or fake. This makes it a binary classification problem using text data. This dataset contains a mix of legitimate news and misleading fabrication content, which allows the model to learn distinguishing patterns between the two categories. Data preprocessing. Before training the models, the text data needed to be preprocessed. This included converting all text to lowercase, removing punctuation and specific characters, as well as tokenizing the text into individual words. For the logistic regression model, I used TF-IDF vectorization, which converts text into numerical features based on word importance. For the LSTM model, I tokenized the text and applied padding so that all input sequences have the same length, which is required for neural network training. These pre-processing steps are critical because machine learning models cannot directly interpret raw text data. The models used. I implemented three different models with increasing levels of complexity. Logistic regression was used as a baseline model. It is simple and fast and interpretable, but it does not capture relationships between words. The LSTM model is a type of recurrent neural network designed to process sequences. It can capture context and dependencies between words, which is important for understanding meaning in text. Finally, I used a pre-trained transformer model from Hugging Face. Transformers use attention mechanisms to analyze relationships between all words in a sentence simultaneously, allowing them to capture more complex patterns in language. Before and after model challenges. One of the key challenges in this project was the LSTM model initially failed to learn meaningful patterns. It produced nearly identical outputs for all inputs, typically around 0.5, which indicates that the model was essentially guessing and not distinguishing between real and fake news. To fix this issue, I increased the number of training epochs, ensured the pre-processing steps such as tokenization and padding were correctly implemented, and adjusted the classification threshold. After making these changes, the model began producing more varied and meaningful predictions. This highlights the importance of proper tuning and debugging in deep learning models. Results. This table shows a comparison of predictions across all three models. Logistic regression often produced probabilities close to the classification threshold, indicating uncertainty in predictions. The LSTM model improved performance by capturing context and relationships between words, resulting in more accurate predictions for complex sentences. The transformer model produced the most confident and consistent predictions, correctly classifying both real and fake examples with high probability scores. This demonstrates the advantage of more advanced NLP models for handling nuanced text data. Evaluation metrics. To evaluate model performance, I use several analytical techniques. The ROC curve shows the trade-off between true positive and false positive rates, providing an overall measure of model performance. The precision recall curve is particularly useful when dealing with class imbalance, as it focuses on the model's ability to correctly identify positive cases. I also analyze probability distributions to understand model confidence, and confusion matrices to identify specific types of classification errors. These metrics provide a more comprehensive evaluation than accuracy alone. Probability distribution. This probability distribution shows how confident the model is in its predictions. Values close to 0.5 indicate uncertainty, meaning the model is not clearly distinguishing between classes. A well-performing model will produce probabilities closer to 0 or 1, showing stronger confidence. This analysis helps evaluate not just accuracy, but also how reliable the model would be in real-world scenarios for decision-making. The confusion matrix. In this confusion matrix heat map, we show a breakdown of model performance. The diagonal values represent correct predictions, while the off-diagonal values indicate errors. This allows us to see not only how accurate the model is, but also the types of mistakes it makes, such as misclassifying fake news as real, or vice versa. Understanding these errors is important for improving model performance. Sensitivity analysis. This slide shows the results of a sensitivity analysis using borderline and ambiguous examples. While the previous results focused on general performance, this analysis evaluates how well the model handles more challenging cases. Logistic regression often produced probabilities near the threshold, indicating uncertainty. This LST model improved performance by capturing context, while the transformer model was the most robust, providing consistent and high confidence predictions across all examples. This demonstrates the importance of evaluating models beyond standard accuracy metrics. Key findings. The key findings of this project highlight the strengths and limitations of each model. Logistic regression is simple and interpretable, but struggles with complex language. The LSTM model improves contextual understanding, but requires careful tuning. The transformer model achieved the best overall performance, producing the most accurate and consistent predictions. Overall, model performance improves as complexity increases. In conclusion, the project demonstrates that machine learning and NLP techniques can effectively detect fake news. While simpler models provide interpretability, more advanced models such as transformers offer superior performance and strength for decision-making in real-world scenarios. Future work could include fine-tuning transformer models, using larger datasets, and combining multiple models to further improve performance. Thank you, and remember to verify your sources.